Hi everyone. So we'll start today's session. So for today's session, we will have a brief recap on the lectures and we'll summarize what we'll be looking into the entire week 2. And at the end, we will look into the practice assignment. Okay. 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 So for we'll be looking into week 2's content today. So initially, we'll begin with a small recap on C programming. So there is an assumption that you all have knowledge on C. So we'll have a brief recap on C, and then we'll move into what is embedded C and what are the strategies for efficiency that we need in embedded C. And at the end, we will look into bit manipulations. So starting with recap on C. So, why did we choose C as language? Because C, so if you see, C is very close to hardware, and so it gives control over system resources. And it can be used in various places like operating systems. So, initially, C was developed for operating systems. So, even the Linux kernel is developed in C. So, yeah, it is used in operating systems. Then it is also used in high performance codes. And then it is used in databases. And it is also used in network applications and game development because of the raw performance that you get from C. Okay. And moving on to data structures in C. So what are the data types that you have in C? So primarily you have int, and then you have character char, and then you have float, you have double, and then you have short, and so on. So for int, usually you have it as 32-bit, and then for char you have 8 bits, and float double are higher versions of the data types that we have, and short is something that you have shorter than the integer data type that you want to use. So in embedded system, you need a very fine data type about how many bits you're going to use. So instead of using a very standard or just a general data type like int, char, and so on, we'll be using very specific bits about how we are using it. So if you see in embedded C, you'll be using something like int 8 underscore d. So if you take this is a 8-bit signed integer data type. And the same thing, there is another u int 8 underscore d. So if you take this one is signed 8-bit integer, and this one is unsigned 8-bit integer. Okay, so yeah, so for embedded C, you have int 8-bit that gives you signed 8-bit integers, and then you have unsigned 8-bit integers, and you also have int 16t, u int 16t. So this gives you signed 16-bit integer and unsigned 16-bit integer. So here for integers, you denote how many bits you are going to give. So the main purpose is we usually do not want to waste the space, so we use specific bits like this 8, 16, 32, and so on. And next, moving on, there are other complex data structures. For complex data structures, we have struct, then you have for enumeration you have enum, and then you have union. So for enumeration, you use this because you want to construct state machine based on the systems, and or you also use it to enumerate different kinds of input and output. So this is in context for the embedded C. Okay. And another recap is you have conditionals and looping systems and conditionals. So if you see, there is if else. So where do we use if else? Wherever there are multiple choices that you have to make. So there you add a condition. If condition is satisfied, then you do a specific task, else you do another task. So, in context to embedded C, so example like you can check sensor value and respond. So, based on how the sensor value is there, you can respond accordingly. So, for that, you can use if else. And another conditional statement is switch case. So, switch case, so this is also a compact way to express multiple choices, like the same way how we saw for checking the sensor values. If there are multiple sensor values, you can add those all in the switch cases, and then you can add it in the response value how you want it to respond. So next, moving on to loops. So there you have for, while, do while. So you usually use for where you know exactly what's the iteration you want to go on, and while do while helps you to have a very uh, let's say whenever you want to use something you're not sure about how many iterations you want to go on, then you'll use while do while. So and then moving on to this while do while, right? So if you're using, let's say, while of one, this is an unconditional loop, so this will never stop. So whenever you want to change the control of this loop, you will test some condition inside, and to change the flow of the control, you'll use statements like break, continue. So break will help you come out of the loop itself, and continue will help you to skip that particular iteration and move on to the next iterations. Okay, and moving on to another important topic is functions. So functions, it is a form of a reusable code. So if you have a specific code that you want to keep on reusing in a later stages, we usually put it in function so that it can be called whenever it is required. So it has arguments and it has return types, and you can add argument based on what are the values you're trying to give into the function to perform inside the functions. And then you can let's say you want to return a specific output outside that function, then you'll be returning it using the return types for that function. And okay, moving on to the next part, that is stack. So stack, it is a specific area of memory that is given to each function call, and it also enables the sense of recursion. So it will have local variables that you need within the function. So whatever the variable the function requires and which is local only to that function will be stored in stacks. And but it also helps to pass the data. So now we have local variables that is within the stack, right? So particular function has local variables that is stored in stack. So that local variable will not be known outside the function. So this type of data can be passed back and forth between the caller and callee. That is, let's say you're calling a function add, and there is a function add elsewhere. So whenever you want to and you're returning, okay, you have int, so and you're returning, let's say x, and here y is equal to, you're calling that value. So now whenever you want to pass this data, so this will be your caller and this will be your callee. right? So whenever you want to pass this data from here to here, so these all happens in the stack. So it will help you to pass data back and forth between the caller and the callee functions. And the next one is heap. So we saw that stack is for local variables, right? And the same way heap, it is for general purpose storage, like even the dynamic memory allocation and all the global variables that is not just for the functions. So these all are stored in heap. Okay. So this is the brief overview of how we have gone through the C programming language. Okay, so moving on to the embedded C topic. So now embedded C. Now, okay. So why do we want embedded C? Right. So the first is it has direct hardware manipulation. So this is one of the strongest reason of using embedded C, because unlike higher level languages, embedded C will help you control the registers, memory and pins directly, and this is really crucial for real-time systems. And the next one is constrained resources. So it's interesting that embedded systems they often run on very limited RAM, ROM, and processing power. So this pushes us to write efficient code. So you want the code to be efficient, so that gets the job done with minimal overhead, or the overhead value will keep on increasing if you do not write efficient codes. So for that you need constrained resources, and because of the constrained resources we subsequently write efficient codes as well. And the third point is it is highly optimized in operations. So this part is also very important because in embedded applications, right, even a small delay or extra instruction will affect the performance, because we want everything to be in real time, right? So optimization is not just for a good practice here, but it is also a necessity here. You have to keep it optimized to get better results, because even a very slightest of the delay will affect the performance. And next one is where do we notice embedded systems? So we practically notice it everywhere. Like in TVs, we have like day to day life, we use it in TVs, then we have in washing machine, and then we have even in cars, medical devices, and so on. So, because of this wide usage, right, in the daily life itself, we're using it in very wide range. Learning embedded C will open up opportunity in, let's say, multiple industries as well, not just one particular field. And also based on constraints, like we earlier spoke about how we having constrained resources, right? So talking about constraints itself, first it's battery and power. So since portable devices must last long, right? So writing energy efficient code is just as important as the hardware design also. So you have to make sure that we're writing energy efficient code. So because of that, portable devices will also last longer. And then moving on to size, uh, always need smaller size. We need it to be compact. So portable devices mean software must adapt to limited space and computing ability also, because we always have embedded C in another system. So to be able to add it into another system, we want it to be compact. So second is size, and the third one is the cost. So every additional feature will keep on adding costs in embedded systems. So that's why optimization isn't only about speed, it is also about how you're trying to reduce unnecessary hardwares. Because whenever you're trying to add additional one, then even the cost will keep on increasing. So these are the constraints you have to keep in mind while moving on to the embedded systems. Okay. And then talking about similarities and differences, just give me a second. Let me add a code here. Okay. Okay. So here we're talking about the similarities and differences in C and embedded C. So there are similarities and there are differences also. So if you see in the first program here, right? So this is a standard C programming that we learn. So input and output here. So if you see the input and output here, it happens through the keyboard and screen. So the program asks the user to enter the test, it stores it in data, and then it prints it back here. So it's also platform independent. It can run on a PC without any special hardware also. And next, moving on to the example of embedded C. So this is your C, and then moving on to embedded C. So here, instead of reading from the keyboard, we are reading from a hardware register here. If you see, we are reading from the hardware register at the address given here. And the key here, you have a keyword volatile. So this keyword tells the compiler something like, do not optimize this variable because the value can change anytime. And it can change anytime because of the hardware events that will happen. So that is why we use volatile keyword here. And here, if you see sensor data, the sensor data might come from a real world sensor. It is coming from a real world sensor here. So real world sensor, it can be anything like temperature, pressure, or even accelerometer, gyroscope, anything, any real world sensor. So the program then uses that sensor value to make decisions. So if you see here, you can make any actions that can be made, like you can turn on a motor or even light an LED, switch on and off LED, so etc. So all these actions can be taken here after getting the sensor values. Okay, so I think this is the main thing about embedded C, right? So instead of talking to humans here, the program will directly talk to the hardware itself. So in normal C, you what do? You input and output is through the keyboard monitor, say input and output. But in embedded C, it is through registers, peripherals like sensors, motors, LEDs, and so on. So it is more or less the logic is the same, but the environment and the purpose that you're using for is different. So here this is a general purpose programming that you're writing, and here this is more specific program that you're writing. Okay, so moving on to strategies for efficiency. So strategies for efficiency. So what is efficiency? So if you're talking about efficiency in terms of embedded C itself, then we care about execution speed. So execution speed as in the real-time response that we get, and then we care about memory usage, that is the RAM or flash that are limited. And then the third thing is about energy consumption. So energy consumption here is more like battery life. If you see the initially we talked about constraints. Where are the constraints? So here we talked about constraints here, battery and power, size, and third was cost, right? So even the efficiency that goes on. The first is about execution speed, so the real time response. The second is about the memory usage, and the third is about the energy consumption. So an example for this can be a simple LED blink. So it must be a very lightweight thing, right? Because the same microcontroller can also be running a motor control, or it can also be reading the sensor value, and it can be communicating between different sensors. So this way a simple LED cannot take more weight there, so it has to be lightweight. So this is some example of how efficiency should be in embedded systems. And why does it matter? Because embedded devices run on constrained hardware. So every byte of RAM, or every extra CPU cycle, that will cost you battery, heat, and also cost. It will cost you money as well. So unlike PCs, we cannot really waste resources here. So we have to make sure that there are specific data types, or even the specific values are being given while writing efficient code. So that is the main key, that is efficient code. So another example, let's say we're having a pacemaker, or let's say a car. So ECU cannot afford delays or memory leaks. So this is how you have to make sure that efficiency really matters, right? And next one is in the terms of efficiency itself. Let's talk about memory efficiency. So when we talk about memory efficiency, then we'll indirectly talk about the data types that we are using. So the smallest integer type that fits the data is what you have to use. So let's say you want to just use 0 or 1. For this particular value, for 0 or 1, you do not go and use integer type there. Instead, we would prefer boolean there, right? So this is what we talk about, how efficient we have to write it. And for, let's say, values from 0 to 255, then we have to use something like unsigned integer 8 bits. So 8-bit unsigned integers is enough, because we are starting from 0 to 255. You do not need signed integers, and you do not need even 16 bits here. So we have to avoid using large types unnecessarily. So this will help us save RAM, flash, and it also reduces the computational cycles. And next, moving on to loops and function calls. While we are using loops and function calls here, we have to make sure the loops are tight and predictable. And you have to also avoid unnecessary function calls, like inline small functions. There we should, like, these are the critical loops. So in critical loops we should not have unnecessary function calls. And we also have to consider loop unrolling. So if you take, also have to consider loop unrolling if it reduces overhead. And let's say for this kind of loop and function calls, example could be like reading 4 sensor values in a single loop versus calling a function 4 times, right? So these are the things that you have to make sure to have a very efficient code while writing for embedded systems. Talking about best practices for efficient codes, we have to keep code modular, but we also be mindful of the overhead, because the code should be readable as well. Because future, when you're trying to read back again, you should be able to understand it. It shouldn't be something like you're writing it now and later you're not able to understand it down few months or so. So mostly we use a keyword. So this is a constant keyword. So you use this for read-only data. So this will save RAM access for you. So this basically is stored in flash. So if you see this const, whenever you use this const, you cannot really write the data here. It is only for read-only. And then we talked about this keyword volatile. So this we use this particular keyword correctly for, let's say, hardware registers to prevent unwanted compiler optimizations. And we also have to avoid recursion because it increases the stack usage, because we initially saw that uh, recursion happens in stack. So to avoid increase in stack usage, we have to also avoid using recursions. And another point is we also avoid using floating point, because floating point is low and expensive on small MCUs. So you have to basically avoid using floating point wherever possible. You have to avoid it. Wherever possible, you can replace it with integer math or fixed point arithmetic. So let's say you're calculating distance. So let's say distance is equal to we're having distance is equal to time into 9.8. Instead of using this 9.8 here, you can multiply it by 98 and then later divide it. So these are the things you can do so that you'll be able to avoid floating point digits. And then moving on to dynamic memory management, so we also avoid m alloc and also free. So these are the keywords that we use whenever we want to free any space or whenever we are allocating any space in the dynamic memory management. So there are two memory management which we will talk about in later: static memory and dynamic memory. So whenever in dynamic memory you want to allocate or whenever you want to free, you will use this. So, but in embedded C, we have to avoid using this because this leads to fragmentation. It will also lead to unpredictability and crashes. So we'll try to avoid this as much as possible. So we prefer static allocation. Static allocation is somewhere you define the arrays and buffers at compile time. There is no dynamic allocation. Everything is already defined. So if only absolutely needed, we use memory pools. Unless and until, we just use static allocations. And moving on to compiler optimization itself. So for the compiler optimization, there are compiler flags, optimization flags that are available like O2, OS. So these are the flags that we use for compiler optimization. And then we check the compiler generated assembly to make sure that there are no waste. And we also use inline functions and register variables wherever there is appropriate. And then we have macros and functions. So we use macros for constants instead of say magic numbers. So example is something, instead of using 100, we already use like you know how to define macros, right? So you write hashtag define, let's say name be speed, and then we write a number. So we define macros instead of using the numbers. And for inline functions, they are better than using function like macros because it is safer and is also more readable. And last is about testing and profiling in terms of efficiency. So we always test early on the hardware because we want to measure memory usage, execution time, and power consumption. We want to do all these. So we use profiling tools or simple, toggling an oscilloscope to measure time. So we also optimize wherever it matters. We just do not go blindly and optimize everywhere. So wherever it matters, we have to go and optimize the code. Okay, so these are about the strategies that you have to follow for efficiency. Next one is about memory management in embedded C. So next one is about memory management. So we already had a discussion about static and dynamic memory, right? So that is what we will talk about here. So in embedded systems, memory is one of the most precious resources that you have. So unlike PCs where we may have gigabytes of RAM, embedded devices often run on very few KBs. So understanding how this work will help you to manage it properly for writing efficient and reliable code. So if you see again and again, it is about how efficient you're able to write the code, and everything is because of the constrained resources. So types of memory, you have three major types you have here. That is RAM, you have RAM, random access memory. So this is volatile memory, meaning that the data is lost when the power is switched off, and it is used for variable, stack, and temporary data. It is very fast, but also it is very limited also. And then second is EEPROM. So this is electrically erasable programmable ROM. So if you see here, read only memory. So non-volatile memory, meaning the data remains even after the power is switched off. And it is useful for storing small amounts of configuration data or calibration values as well. So here you have downsides, that is it is slower, that is the writes here are slower, and it also have very limited write cycles. So the third point is flash or program memory. So this is where the program code itself is stored. The entire program code that you're writing, that will be stored here. So it can also be used for constants and lookup tables. It is larger than EEPROM, but still limited compared to the PC systems. It cannot be at par to PC systems. So, memory management, talking about memory management in embedded C, so it is about deciding how and where variables are stored and accessed. So, unlike desktop applications, right? So, embedded system must carefully control the memory to prevent any crashes or any unexpected resets or high power usage. So, this is what we tell whenever we talk about memory management in embedded C. So as we spoke about, so we have static memory allocation, and then we have dynamic memory allocation. So for static memory allocation, it means that all the memory for variable is decided at the compile time itself. During the compile time, all the allocation for memory for variables is already decided, like for global variables or local static variables and array with fixed sizes, these all are statically allocated. So if you want example, then example like int buffer of 10. So this is already allocated at the compile time. So advantages here are it's very predictable. The memory size and locations are fixed before the execution itself. So there are no fragmentation. So it is safe for the real-time application, and it is faster. Since allocation and deallocations are handled by the compiler itself, right? So it is faster. The downside is it is not flexible. So if you want to allocate let's say something you have allocated 10 but you want too much, like if you want 15, then this is not flexible. So here there will be an error. So if you allocate too little, that is like here the program may not run, and if you are say that you're allocating too much, then the memory is wasted. But here we do not want to waste the resources. So it is not suitable when memory needs change at the runtime. Unless and until there is no change, this static allocation is fine. So for that we have dynamic allocation. So this allocation means memory's allocation at runtime. Here it is for static it's allocated in the compile time. In dynamic it is allocated in runtime. So whenever you want to allocate, here it is done using the function which we already saw here, the memory allocation function malloc. So we use this function to allocate the memory there, and then it can be freed using free function. So these are the two functions that is important in dynamic memory allocation. So if you see, there are various advantages also, like you can allocate memory whenever you are needed. So it is a flexibility that you have here. And then it is also useful for data structures that grow a string, like let's say you have a linked list or even a variable size buffer. So for these all, this is useful because it is flexible. But there are downsides when we talk about embedded systems. That is, this causes fragmentation, so which is dangerous in small memory environments. So allocation time is not predictable here, so which is also bad for real time systems. For real time system, we want to know the time, because of which we do not want any delays there. So that is why we are telling that allocation time is not predictable, and that is dangerous for real time systems. And you also have risk of memory leak if the memory here is not free. If it is not freed here, then even there is chances for leaks. And also there is also about optimization in dynamic allocation. So we use fixed size memory pools instead of general purpose mloc. So that is what we initially told when we were talking about efficiency, that we prefer to use static, and when and only necessary we use memory pools. And we also limit the number of allocations and deallocations. We try to keep it to very minimal as possible. And we also check for null pointer returns. Whenever there is any null pointer return, we make sure that is handled properly. And we have to always make sure whenever we're using dynamic memory here, we also have to free memory as soon as it's not needed. It should be done immediately. Okay. So these are all the overviews about how what is the embedded system, and what are the memory allocations here, what are the memory managements here, what are the strategies we have to use for writing the code efficiently. So talking about bit manipulation, which is a important topic in embedded C, is bit manipulation. Okay. So here, as we already talked about in embedded C, we don't just work with variables, but we also work directly with hardware itself. And hardware is controlled through bits inside registers, and bit manipulation is about how you're trying to read or set. You can do like read, you can set, or you can clear, or you can even toggle those bits. Okay, so this is all about the bit manipulation. So why do we need bit manipulation? Because we want to control the input output pins. So we want to control the input output pins. And why do you want to control the input output pin? So something like turning on led or turning off led, these all can be done by controlling the input output pins. And the next one is, why do we need bit manipulation, is to configure the peripherals. Like for whenever you want to peripherals, okay, so whenever you want to configure, say, UART baud rate, so these are the terms which will come later weeks. So this is something you can remember for now. So peripheral, something like UART baud rate, ADC settings, so these are something you learn going on using the hardware itself. So these are different peripherals, and to configure these peripherals, you will need the knowledge of knowing how to do the bit manipulation. And then next one is to handle flags. So you have different flags, like there are error bits, then you have interrupt status. So these are the different status and error bits you'll be talking about. So like, and to handle those you need bit manipulation, so about handling flags. And then at the end it's about saving memory. So as we talked about again and again, everything is about constrained resources that we have, so we have to make sure we save memory. So using a single bit instead of a complete, full variable, that will help us save memory. So instead of storing 8 boolean values in 8 bytes, right, we can store them in 1 byte and manipulate bits. Because what like let's say you are having 8 boolean values. So boolean values is 0 and 1, right? So if you're having, that is equivalent to 8 bits. So instead of storing this 8 bits in 8 bytes, we just store it in 1 bit. So in 1 byte, so we store it in 1 byte, and in this 1 byte you will have 8 bits already stored. So those 8 bits that are given, that can be toggled, set, or any manipulation can be done in those. So this way you can save memory. And okay, now moving on to the bit manipulation itself. So first you have and. So this will help you to clear or check bits, like you can use reg. So this one will help you to clear bit. So which bit? It will help you to clear bit 2. So this is 1, and this function here, this will help you to clear bits. So what does this mean? This is something like register is equal to end not 1. Okay, so this will help you to clear the bit. Clear which bit? It will clear the bit 2. And then you can also check if bit 2 is set. So how do you check if bit 2 is set? You can use if stir and 1 2. So this will help you to check. So here if you see this AND operation here, so this will help you to check if bit 2 is set. So this is for checking. So here AND is used for clearing the bits, is also used for checking. And the second one is OR, the symbol, this one. So this will help you to set bit. So to set bit, what you have to do? Reg or equal to 1 5. So what will this do? This will help you to set bit 5. If you write this, then this will help you to set bit 2. Okay, so this is for OR. And then,
Excuse me.
yes,
Uh, ma'am, like, what is one representing there? Like, a one is less than five. So then, like, one, what is one representing? The starting position of the bit.
sorry, I cannot hear you.
Uh, Ma'am, I'm asking
Mm-hmm. Yes, continue.
that, ma'am, like, what is one representing here? Like, one is
This one.
less than. Yes, ma'am.
Okay, so if you see here, this one, this will help you to represent how, like, say, so you have for boolean you have 0 1, right?
So, ma'am,
Can you
this is the
hear?
first bit.
Yes, go on, go on.
Ma'am, this is the first bit of that. Like, suppose we have a number 10. So, like, this is
Mm-hmm.
the first bit of the binary representation of 10.
What do you have? First bit.
Like, suppose we are having a decimal number 10, and then, like,
Mm-hmm.
if we take out the binary, take that number in the binary form, then 1 is representing the first bit of that binary form.
Yes. So let's say you are having an expression 1 tends to n, right? So this will generate let's say a bit mask where only nth bit will be set to 1. Did you understand?
Yes, ma'am.
So if we're having so let's say, so we're talking about or, right? So let's say x is equal to, okay, x or 1 gives you n. So this one, it ensured the nth bit was 0, it becomes 1. So if the nth bit was 0, then it becomes 1. And if it was already 1, then it will remain 1.
Okay, ma'am.
Okay, so this one is not about the what you did, first digit or second digit. So this is what we are talking about, nth digit. So here, this one is something where you have Boolean values, right? 0 and 1. So that one.
Okay, man. Got it.
Okay, so everywhere, not just here, even initially you had here, right? So this is also, it's the same thing. So here you have AND operations. So it's about if the second bit is 1, then the operation is performed there using 1. So let's say here, if you're having if x and 1 1, so this will be what? So to check the nth bit of a variable, that is what this nth bit of variable is set. So you can use an if statement here to check that. So if we are checking if it is set. Okay, is it clear now? Like why we are using one? So one is something that we are using
Yes, ma'am.
to check or set or toggle the bit. So for or, that is how it happens. So for or, whenever, let's say nth bit, so here we're talking about fifth bit. So whenever the fifth bit is 0, it becomes 1, because 0 or 1 is what? 1, right?
Yes, ma'am.
Yes, and 1 or 1 will be 1. So that is how this function. And the same thing, or 0 or 1 will be 0, 1 or 1 will be 1. So how do you think this will test? So this will test like the nth bit. Let's take the same example of 2. If x 1 tends to 2, then we are trying to check if the bit is set. So whenever the second bit, that is the second bit is 0, what happens? It gives you answer as false, that is not set. And whenever the second bit is 1, it will give you answer true, which is set. And why it happened? Because it is getting an and operation. This and or all the operation of bitwise operations. So whenever you have this 0, the second bit and or this 1 happens, and that will give you 0, and 1 will give you 0. So that way you get result as not set. So this one is something which you're using for the bitwise operations. Okay. So
Yes, ma'am.
yeah. So we were talking about or. So for or, we use it to set their bits. So this is the one which you talk about nth bit. This one will give you which location you have to check, and this is a usual value one. So and then so this will help you to set the bits. Third one is XOR. So this one will help you toggle bits. So the function goes like reg XOR equal to 1. So I hope you all understand this notation, right? The shorthand notation for reg is equal to reg XOR 1 times 3. So this will help you to toggle the bits. Toggle the bits as in, so if you're having, let's say 1, it becomes 0. If you're having 0, then it becomes 1. So here also the same thing. Will be the third bit here will have, let's say, we'll take this as n, then this n will have XOR with 1, and you will get an output here, either 0 or 1 based on the n value. So that will help you to toggle the bits. And then finally you have not. So not
Excuse
will
me,
help
ma'am.
you to invert all the yes.
Uh, Ma'am, in the XOR, like if the third bit is zero, then it would become one, and
Mm,
if it is one, then it would become zero.
yes.
Okay, thank you, ma'am.
Yeah. So, how does it happen is because of the XOR table. So, what is the XOR table? 0, 0, 0, 1, 1, 0, 1, 1. So, what is 0, 0 here?
1.
0.
0, 0 is 0, right?
Yes, ma'am.
XOR table. Okay. And 0, 1 is 1. 1, 1 is 1. 1, 1 is 0. Okay.
0.
So, based on this table, you will get here what. So you have a certain value which is always 1, right? So this 1 is this one. And your nth bit, if it is 0, it becomes 1. If it is 1, if it becomes 0. Okay? Is this clear?
Yes, ma'am.
Okay. Okay, so this is that is about toggling the bits, and next one to let's say invert all the bits. So this here we are talking about each bit, right? So in, let's say you're having 8 bits, so in 8 bits, that is 1 byte, we are talking about toggling third bit or fourth bit and so on. And now if you want to toggle all the bits, that is invert all the bits, what you do, you have to just use not, and this will help you to invert all the bits, every bit. And the next one is shift operator. So this will help you to move the bits, like if you're using let's say this 1 7, then this will help you to move what do you think this will help you to move? What happens in the seventh bit? Any guesses? Any idea?
The 7th bit would move, like, right shift the 7 bit by 1.
No, here if you see, it will move 1 into, so this one will go into the seventh bit. If you're using 0 and you're writing move, then it will help you to move 0 into that seventh bit. And next important one is about bit mask. So, bit mask, it is something like a pattern which is used to isolate or modify the bits. So, let's say we are having an example like, first we will write a macro for bit 3. So, here we are writing a macro, then you're writing register or bit 3. So, what do you think this will happen when you're writing register or of this? For or what did we tell was happening? Which particular bit manipulation was happening for or?
The third bit manipulation.
Yes, third bit manipulation, but what it is clear bit or set bit or toggle?
Set bit.
It's the
Correct.
set bit.
So it is set bit. So what happens? It is set bit 3. So it happens, the set operation happens on bit 3. And next we are talking about uh, let's say end. So register and equal to not bit 3. So what happens here? So we talked about registers and equal to not of this particular macro. So what did we talk about? What kind of manipulation was happening there?
Clear and
Sorry?
Reading the bit 3. Clear. We're not clearing the bit 3.
Yeah. So it is, we are clearing the bit 3 here, right? So where is it? So yeah, first initially we spoke about clear and check. You see here register and not equal to, here we are clearing bit 2, right? Here in the example we are clearing bit 2. So the same example here, we are doing using a macro for bit 3. So this is a clear bit 3 manipulation. So here it is always useful here for readability. So wherever we are writing this particular 1 tends to 3, right? So wherever we want to use it, we just define it in macro because this will help in terms of readability, and it is also easier for writing. If you want to change it, you can just change it in one place and every place gets changed automatically. So and also we have to make sure that we also have to define the masks, that is the names with meaningful name, because only when it is a meaningful name you'll be able to understand it later stages, or maybe down 3 months you'll forget everything about why you use that particular macro itself. Okay, so next, okay, I will add an example here that we will, or okay, okay, just for now, let's just have a simple example about what kind of problems might come up in future weeks and so on. So, understand that we do not have a detailed understanding of the entire embedded C program, but a small example we can have about, let's say, GPIO. So here, let's say we are trying to like switch on and off the LEDs. Okay. Yeah, give me a second. So yeah, now talking about switching on and off LED, it can be done using bit manipulation. Like, what is the main idea behind it? We try to switch on using, whenever we set it to 1, it will switch on, and whenever we again toggle it to 0, it switches off. So the main thing is about how we are trying to move from 0 to 1 and 1 to 0 to let's say change the LED to on, off, and so on. So so yeah, so it's based on toggling and setting bits. So any idea on which kind of operator we can use, like not the entire program itself, but any idea on that particular line where we are trying to, change the LED from 0 to 1 and 1 to 0.
Then we can use the OR operator.
Yes, we can use the OR operator. Okay.
One can be also used to XOR. Like,
XOR. XOR is, yeah, we can also use that also. Yeah, we can use XOR also. We can toggle bits, right? So you can use XOR also, and you can also use and also. Okay, so let's say here, first maybe you can define uh, what let's say LED pin or something, like any name that we want to give, we can give. And what do we want to do? So we just have one, right? So we have just one bit because we are using just one bit. We are trying to toggle only one bit. So for the 0th bit, we are trying to toggle. So we are using 0 here. And then for 1 is about how you're using 1. So as we have seen, everywhere we'll be using 1 because using this 1 and performing functions like and or XOR or these all gives you unique manipulation that you can do. Like here you can check bits, clear bits, here you can set, here you can toggle using the same one. Okay, so here you define, and then let's say you if you're having, let's say, port, so in a port, so all the LEDs, if it's connected in a port, so in that particular port, if you perform an OR operation to this, what do you think will happen now? Yes. So if you're using a OR operation and you're using to zeroth bit, what will happen? And let's say initially you're giving bit as 0. So initially if it is 0 and you're giving this, what will happen?
It will set the bit to 1. Sorry, 0.
Correct. So yes, correct. Good. So it will turn the bit to 1. So when it becomes 1, it will turn on. Right. So next, if you are trying to, let's say, switch off, and you're using port A, and then you're using uh so okay. So what do you think this happens?
It will clear that bit.
Yes, it will clear. So clearing is what?
Off, madam, switching off the LED.
Yes. So when you clear the bit, it will switch off. So it can be done this way also. And as one of you told, you can use XOR also, because XOR will be helping you to toggle the bits from 0 to 1 and 1 to 0. So even that can be done. So let's talk about that also. Like, so if you're using port A, like you can forget this for now. So if you're using port A XOR LED pin, then what happens now?
It will toggle the bit. So
Yeah.
0 to 1.
Okay. Yes. So it will toggle the bit, right? So it will 0 to 1. So 0 to 1 on. Same thing. And it goes to the same thing if you write again, it will go to off. Okay. So, yes. So I guess, yeah. So this is about a very small example about how you can use the toggling bits and all. And you can also do something like packing multiple flags into one byte. So like, so let's say you are having, okay, like you're using a unsigned 8-bit integer flags, and so 8-bit, right? So you're giving it as 0. Next is you're using uh, flags. So using OR operation and performing that on 0th bit, what happens? So this is a 8-bit. So this is what? 8-bit, right? So what happens here? It will set flag 0. 0, right? 0. And let's say we are doing for flag and we are doing again, but for another nth value, let's say 3. What happens here? Here becomes set flag 3, 3rd bit. And let's say if you're using the clear operation now, and you're using the clear operation, this will clear flag Which bit? 0th bit. So it will clear flag 0. So these are like what very and memory efficient. And so if you see, you're using this bit manipulation because you're having it in entire one particular byte. So these all bit manipulation can be done to save memory, and you have memory efficient, and these are also common in protocols as well. And okay, so talking about best practices, we have already talked so far. So you have to always use unsigned integers for bit manipulation. You can use macros or enums for bit positions because that will help the to improve the readability. So it is easily readable. And you can use volatile for hardware registers because that will help you to make it understand that anyway the changes will be performed because of hardware events. And then you have to always keep the code portable by avoiding any hard coded number. So if you see, everything will be added in the macros itself, there is no hard coded numbers, so these are helpful to keep your code efficient. Okay. And there is another important topic in embedded C, that is pointers. So another important topic. So these pointers are also one of the most powerful features of C, and especially in embedded C, right? So they are even more important because this pointer will allow us to directly access the memory. So it will help you to directly access the memory. And when you can directly access the memory, you can work with the hardware registers and you can pass on the data efficiently and so on. So if the bit manipulation is like, let's say, important, then this pointers is even important than that because they can just directly look into memory and give you direct access over there. And what is pointer talking about pointers? First, we want to know what are pointers, right? So, what are pointers? They are simply a variable that stores the address of another variable. So, for example, let's say you have int x 10, and then you have int star p and x, and then okay, so for this, what happened? This x is a variable that stores value 10. So this will store value 10. And what is the star p that you have here? This will store the address of x. This will show how it here, the x. So this will help you store the address of x. So if you see here, x holds the value of 10 and ampersand x. This will give the address of x, and p will hold the address of the p will hold the address of x. And then you have star p, which will help you to go to that address, and from there x will get its value. So star p will give you the value that is stored in x, so that will give you 10. Okay, so pointers are like the important tools that we have to read and write the memory directly. And why do we have pointers in embedded C? Because in embedded C, pointers are essential because you have hardware registers are accessed by their memory addresses. As we told, there are different peripheral devices like UART, ADC, and so on. So these all are controlled through pointers, which we will talk about in later weeks. And also efficient data handling. So instead of copying data, we just pass around the addresses, right? So here, if you see, p star p got 10 just by passing the address of x. We are not copying the values each time. So if you talk about dynamic memory, This is also possible through pointers. Dynamic memory, if we are using it, it can be done using pointers. So, and also pointers, if we're talking about pointers, pointers and arrays are also very closely related, right? So, if we are, let's say we are talking about, okay, yeah, unsigned integer 8-bit array. Let's say we're having 5, there we're having 10, 20, 30, 40, and 50. So this is an array of 5 elements here, and then you have another pointer with same unsigned integer of 8 bits pointer, which gives you array here. So if you see this here, this array here, this will give ptr will hold the address of array here, and star ptr will help you to get the values here in the array. So here, array of 0. So what is the value of here?
10.
Okay, yes, 10. And if we are talking about star ptr, this will also be 10. And if we are talking about array of 2, which will be equal to, so this will be 0, 1, 2, that is 30. Then here, star ptr plus 2 will also give you 30. So this is how array and pointers go hand in hand. So whenever you're using pointers here with ampersand to denote for array, you get the value, and if you're adding the same number of indexing here, that will give you that particular array value. So this is a very useful relationship that you have to keep in mind whenever you're working with buffers and like communication protocols, like serial. You will learn about it, like serial, UART, any communication protocol that you're working with. This is a very important thing you have to remember. And another advanced topic is that function pointer. So pointers can also point to function. So this is also very useful in embedded systems for like callbacks and interrupt handling. So you have something called function pointers. So what is function pointers? Is the pointer will point to the function. So this is useful to for what callbacks. It is useful for callbacks, and it is also used for let's say interrupt handling and so on. So interrupt handling, interrupt status, these are the flags also you have for interrupt. So these are the things which you will be learning more in embedded systems programming. So these are the ones which you need to go through the entire embedded system programming. And talking about best practices in pointers, you always have to initialize pointers before using. So if you see here, we did initialize, right? So you always have to initialize before using here. So you have to use the data type also correctly, like your what unsigned integer 8-bit or signed bit 8-bit, and so on. So you have to make sure that you're using the correct data type and use the variable const. So you have to use this variable for like for constant. You have to use this, sorry, this is not a variable, this is the keyword. So you have to use this keyword for pointers for read only data. So wherever you have read only data, you have to make sure you're using this. Then as we already spoke, you also have to use volatile keyword wherever necessary. And you have to never dereference an invalid pointer, because whenever you're dereferencing it, it will crash the entire system. So you have to make sure you have to not dereference it. If you have referenced it, fine. But if you're referencing an invalid pointer, then that will crash the system. Okay, so this is a very basic gist and summary that we have for week 2 about how we are getting introduced to embedded C from C programming, like basics of C programming. Then there are like basics of embedded C, how you have to write the code, what are the strategies you have to keep in mind to make sure that you have efficient codes. Okay, so these are for the yeah, the basic thing. So I think now we can go through practice assignment. I will add the just give me a second, let me add it here. Okay, so here now this practice assignment for week 2. So the first question is about primary benefit of using fixed point arithmetic over floating point arithmetic. So, yeah, what do you think it is? Increased code readability or computational accuracy or power consumption and execution time? Okay, so we did talk about floating point arithmetic, right? So, here, if you see your reduced power consumption and execution time, because floating point math is expensive in embedded systems, because not all microcontrollers have hardware floating point units. So fixed point arithmetic uses integers to represent the real numbers, so this will help make the computation faster, so faster execution time, and it will also reduce the power consumption. So the correct answer will be reduce power consumption and execution time. Accuracy is often slightly less, but efficiency is the goal. The goal is you should have highly efficient code, and because of that, as we already spoke, we talked about distance example, right? So whenever you wanted to distance t into 9.8, what do you have to do? You have to do t into 98, then later you divide it, right? So this is for the first one. Second one is about best practices for the memory management. So what are the best practices for memory management to improve code readability and maintainability? So out of the options here, you have to like first is using global variables, second favoring dynamic memory, third is utilizing local variables, fourth is implementing complex memory. So which do you think you is the correct answer? Anyone? Okay. So here for the second one in embedded C, we want readable and maintainable code, right? So using local variable will keep the scope limited and it will avoid bugs that arise from global variable. So this way, passing argument will make code modular and easier to test. So the best practice here will be to use local variables within the function. So this will help the code to be modular and easier to test. And talking about third, third one is about common use case for enum. in embedded systems. So here, if we talk about common use case, what are the common use cases? In embedded system, we often deal with states like idle, running, error. So these are the like states that we will be looking into. So instead of using raw numbers, enums will give you meaningful names to those states. So that will help the code make more readable and even maintainable as well. So whenever you want to name integer constants for the state, you will use it. And moving on to fourth one, so for the code output here, so output here, if you see in little endian, the least significant byte is stored in first, right? So ASCII value of 65, what is the 65 for 65? What is it? A, right? For A, the ASCII value is 65. So when we print as a character, what will it print? Whenever if you want to print as an integer, then fine, this will be printed. But if you're printing as char, it will print A. So your answer will be A. And moving on to fifth one. Okay. So yeah, moving on to fifth one. So in this question, they're asking us to assign address. So which correct way to assign memory address which stores one byte to the pointer directly. So which way is it? So we were talking about how to initialize pointer, how to assign values to the pointer, right? So if we're asking here for character, we have to make sure we are also im- changing it to character, and then we have to assign it. So to assign an address directly, we must have to cast it to the right point type. Okay, so you have to cast it, and only this particular one is casting it correctly. So here, this will be your answer for this one. So in other, you can see that it's either not assigned a value, or it is just assigning a value and it is not assigning an address. Or so if you see, this is not assigning an address, this is not it, so this is not assigning an address, and this is not an address. So also there is this here, incorrect casting is done here, so this one will be your correct answer. So moving on to the next one. So increment a float pointer by 2. So in pointer arithmetic, adding 2 will mean that you're moving forward by 2. We saw that while using an array, right? So whenever you're adding plus 2, it will help you to move forward by 2 elements, not 2 bytes. It's about 2 elements. So since FP is a float pointer, FP, here if you see, FP is a float pointer, and FP plus 2 will help you to move 2 floats ahead. So this will be your correct answer. And the next one is, what is the result of 5 and 3? So what is 5? So 5, what is the bit for 5? 0, 1, 0, 1. And for 3 it is 0, 0, 1 and 1. And if you perform AND operation, what happens? 1, 1 is 1, 0, 0, 0. And this one will give you 1. So the answer is 1 for 7. So for 7, the answer is 1. And then the next question, okay. So for eighth question, what does the expression do? So we even talked about this bit manipulation here. So if you see here, they're using OR. So consider the bit positioning is in zero indexing. So what do you think the values is? So what does this OR do? We were talking about OR, right? So what does OR do? So OR will help you to set the bits,
Bit.
right? So here, yes,
Option 3.
yes. So this will help you to set the bits OR. And if there is, let's say, XOR operation, what will that do?
Toggle the bit. Option 2.
Yes, that will help you to toggle the bit. Correct. Moving on to the next one. So here they're asking us the result. So 0x here represent hexadecimal, right? So they're asking us what does the result for this mean. So here if you see, this is a shift operator. So it left shifts and it moves left. So if you see here, you're having 0, 3. So what does this have? 3 will give you 0, 0, 1, 1. So whenever you want to do left shift and here and it says 2, you have to move 2. 1, 1, 0, 0. And what is this value? This is 2 power 0, 1, 2. This will give you C, right? Because this is hexadecimal value. 0x, 0, C. So this will help you get 0x, 0, C. And finally, they're asking question on dangling pointer. So what is a dangling pointer in context of embedded C programming? So a dangling pointer refers to an invalid memory location. We were talking about how you have to not dereference the invalid pointer, right? So the dangling pointer will refer to an invalid memory location. It will refer to invalid memory location. So, for example, a pointer to a local variable after the function ends, right? If there is a function and pointer for a local variable, say x. So, if a pointer is there to this local variable x after this function is ended, it is not out of scope, right? For this one, local variable will have scope only within the function. So, once the function is over, then the pointer to that particular function will become a dangling pointer because that is an invalid memory location. So accessing this can cause undefined behavior, and this is also a very big risk in embedded C. So this kind of problem here we call about a dangling pointer. So a dangling pointer, if you see here, wait, let me bring up the options here.
Excuse me.
Yes, so here are the options for the dangling pointer. So null address, then you're having a memory location which has been freed or is out of scope. Then you're having location not initialized or volatile variable. So which option do you think is closely related to the one which we discussed with an example? The out of scope, right? We just talked about an example where there is a local variable x, and whenever there is a pointer that is pointing to x, once the function is over, then it will go out of scope. right? So this is an invalid memory allocation. So this is what point dangling pointer is. That a pointer that points to memory which has been freed or is out of scope. So I guess this is all about week 2. So in week 2, we did discuss about a basics of C, then basics of embedded C, strategies for efficiency, then about different memory management and memory allocations that are present, then manipulation that are needed in embedded C, and finally we discussed the practice assignment. Okay. Okay. So any doubts you have? Okay. Then if there's no doubts, yeah, then we can close the session here.
Okay, ma'am. Thank you, ma'am.
Thank you. And today is the deadline for